Good afternoon, everyone. Today, the Admin Seminar has the great pleasure of welcome back Professor Gabriele Sadowski. Professor Sadowski is a renowned scientist and professor of thermodynamics at TU Dortmund University. She holds a PhD in physical chemistry from THLM and is internationally recognized for her research on the thermodynamic properties of complex systems with a special focus on pharmaceutical molecules. She received the prestigious Gottfried Wilhelm Leibniz Prize in 2011 and currently serves on the Scientific Advisory Board of the Journal Molecular Pharmaceutics, as well as the German Science and Humanities Council. Her group has made significant contributions to the development of the thermodynamic model PCSAF. So, once again, welcome back, Professor Sadowski. Thank you so much for accepting the invitation. It's a pleasure to have you here with us. Please feel free to start your presentation.
Today, I would like to talk about how thermodynamics can explain unexpected and also unwanted release behavior of tablets. So what has this to do with thermodynamics? The problem is that we are talking about APIs. This is active pharmaceutical ingredients. So this is actually the molecules who have the pharmaceutic and therapeutic effect, and they usually have a very low water solubility. What is found and can be also shown is that amorphous APIs are better than the crystalline ones in terms that they have both a higher solubility in water and also a faster dissolution rate. And that makes a huge difference when we take a tablet, and, for example, containing those molecules. So the idea is to keep the APIs, which are usually crystalline at room temperature, amorphous. But the problem is that the amorphous state is the thermodynamically less stable one, and so the APIs want to recrystallize. So we have to avoid this. And this is, can, for example, be done by dissolving the APIs in a polymer. So if this is really dissolved, it's obviously amorphous. And this is what we then call an amorphous solid dispersion, or from the viewpoint of a patient, it's a tablet. So this is actually a tablet that contains the API molecule, but also on top of this, usually a polymer, so that we have something that we have in hand and can take and eat. So we have these two molecules, and we call this ASDs, and I will now also use this ASDs for short in the for this seminar. So we have an easiest case, a two-component system. We have the polymer and we have the API, and we have a certain solubility of the API in a polymer. So we have the solubility line, which starts here at the melting melting temperature of the API, and then goes this way. So that means the best thing is if to have to know this line, because everything that's right of the line is super saturated. So I have on the x-axis the weight fraction of the API. This is what is usually called the drug load. Makes sense. For therapeutic effects, we need a certain drug load, so a certain amount of API in a polymer, means in a tablet. And for that, it's important to know what the solubility line is, because everything right of the solubility line means that the API will crystallize. This is what we do not want to have. But on top of this, there might also be a liquid-liquid phase separation, or an LLE, and this is usually called thermodynamicists, pharmaceutic people call this amorphous phase separation. We would call this an LLE, and this can also happen for those systems. So the best thing for a tablet means stay outside. So because this means that we are at those concentration and temperature areas, the system is not supersaturated, it's thermodynamically stable. The bad thing is usually the temperature we are dealing with, body or storage temperature, is far below the melting point. So we are down somewhere here, where the solubility region is smallest. And unfortunately, this is not enough. The drug load is given by the therapeutic dose, and usually this is either here or there. So that means these systems are usually not stable in the sense that they will change over time, either by crystallizing the API or by demixing in a tablet, or both, which is both unwanted. And for that, it's important to know, of course, where the solubility line and the LLE line is. This is in a dry system. So we have no water in a system nowhere. So this is for the dry system, but for the storage, it's of course usually storage at room conditions. So where we have a certain RH, for example, 60% or 75% if it's quite humid. And that means that now we have three components in the system. We have the polymer, we have the API, and we have water. And the water will change the solubility line. So this was what it might look like for a dry system. And for the dry system, this point would have been crystallized, whereas this point for the dry system was left of the solubility line, so was safe, so to say. But if we now have a tablet and we store it at humid conditions, it will absorb water. And as the API is very hydrophobic, the polymer usually is much more hydrophilic. The low drug load samples absorb much more water than the hydrophobic ones on the right-hand side. So that means for our tablet that this point, which was safe at dry conditions, now at humid conditions after water absorption becomes supersaturated, because now it's far right of the solubility line in a water-containing system, so and it will crystallize during storage. That is something one would like to avoid, and so that means we need to know where the phase diagrams or how they are, how they look like in the absence or presence of water. And this is what we did. So, for example, this is for a dry system, ibuprofen, which you know is a nice API, and this is a polymer which could be used for formulation of tablets. And the advantage of PVP is that it has a high solubility for a lot of APIs. So what you see is this as data points we have measured, and this is our modeling using PCSAFT, that let's say at room temperature, we can have a drug load as high as 0.4, so meaning 40% of the tablet can be the API, which is very high. And so still this system would be stable, so we would not have to be afraid of crystallizing of ibuprofen in this ASD. However, if we go to higher temperatures, this changes. What you see here is, this was our PCSAFT calculation, that we prepared samples at 25 degrees C with different drug loads, and then we stored the samples. And from time to time, we made a PXID of the samples, and what we saw is that the samples right of the solubility line did indeed crystallize, and the numbers you see here, these are days. That means these two samples crystallized after 160 days, whereas the other ones remain amorphous. This is clear for those because they are left of the solubility line. They will stay amorphous forever. So this is a safe region. This sample did not crystallize, at least not within 3 years, which is, so to say, the time of a PhD thesis. So this sample did not crystallize, but of course, this is also the one compared to the other two, which is closest to solubility line. So the driving force for crystallization is lowest, and we expect the sample to crystallize. This is at dry conditions. If we go to 75% RH, then our prediction says that we have a solubility line, but now we also have a liquid-liquid demixing. And the liquid-liquid demixing again happens on the left-hand side, and this is because this is where the polymer is. And the polymer is the one that absorbs a lot of water at high RH values, and that means here in samples on the left-hand side, we have much more water than in the hydrophobic ones on the right-hand side. And so we expect, the calculation says, this system will demix at the hydrophobic or the more hydrophilic samples, and these are the ones to the left in this diagram. And to check whether this is right or wrong, we again prepared samples having different drug loads and stored them at 40 degrees C and 75% RH. The reason is that the pharmacists have two different types of conditions where they have to store the samples and then to make sure that they stay the same. One is 25 degrees centigrade and 0% RH, and the other one is 40 degrees centigrade and 75% RH. So there are standard conditions for a pharmaceutical company where they have to store the samples over several months to show that the samples don't change during storage. Otherwise, you cannot bring them on the market. So that's why we have the samples here. And this is what we found. The samples we predicted that would demix, really demixed already within 1 day. The ones right off the solubility line did crystallize. Also, again, from the right to the left. That means driving force for crystallization is highest for the ones more far away from the solubility line. This is after 5 days. This is after 8 days, and this is after 440. And the safe samples, so that neither crystallize nor phase separate, are indeed the ones in the middle, as predicted. So surprisingly, for the pharmacists, not the very low drug load was keeping the system stable, but the ones in the middle. And this corresponds and agrees with our predictions. Then what we usually do is we have confocal Raman spectroscopy. So that means we scan the samples in steps. What you see here, this is the total length is 100 times 100 microns. And we can make scans in steps of 2 microns in the 2 directions here. And then the content of the ibuprofen is color-coded. Red means high content of Ibu, and blue means low content of Ibu. That means polymer in this case. And this was done for this sample. So it was supposed to have a drug load of 20%. And what you actually see is that no single point in a tablet has the supposed or desired drug load of 20%, but instead of that, we find droplets having much higher drug load, and then the continuous phase is the one which we have a lot of polymer and has a very small drug load. So this is about 40%, and this is about 5 in average, we would say, for the 2 phases, and this very nicely agrees with the points on the binodal, which is about 40% and 5%. So this says that the prediction is not only qualitatively, but even quantitatively correct. And although we don't have crystals in the system, this is still an unwanted behavior, because if you want to break the tablet into 2 halves, because the doctor says take only half a tablet per day, then as a pharmacist, you have to guarantee that each of the half tablets contains the same amount of API. And this is, of course, hard to do if you have a demixing and inhomogeneous system. So that means that even amorphous phases that do phase separate is something that you would not like to have for a tablet. So it's very important to know the phase behavior, not only at dry conditions, but also at storage condition. And what we can keep in mind is that water is, I would say, an enemy to pharmaceutical products as long as we talk about tablets. So this is something pharmacists really do want to avoid during production and also particularly during storage. So that's why you have the tablets in a blister. So that simply keeps the amount of humid air to a minimum. And that means that as long as the tablet is in the blister, there's no contact to a humid atmosphere. And this really then ensures that the tablets stay the same and stay stable for at least 2 years. This is what the pharmaceutical companies have to demonstrate. So we keep in mind water absorption into a sample is something we don't want to have. So this is for storage. And now we come to release, because this talk is about release behavior. That means I have my ASD. Here the polymer is PVPVA, which is a copolymer of the PVP polymer, which we have seen on a previous slide, and polyvinyl acetate. This makes the polymer a little bit less hydrophilic. And the reason is we do not want that the polymer and the ASD absorb so much water during storage. And so they make the polymer a little bit less hydrophilic. And this polymer is quite often used for tablets, that means for ASDs. This is the API. This is indomethacin, for short INT and PVPVA. And then you want, of course, not only to take the tablet and to store the tablet, but the tablet also needs to be dissolved in the body. And this is what is called release behavior. So I have an aqueous environment in the body, and I now want to release and dissolve the tablet, and I want really to get the compounds of the tablet into this aqueous medium. And this is what we see here. This is time on the x-axis, and this is the release of the different compounds. One means everything is released or dissolved. This is 100%. And what you see is here that both components that are in the tablet, the polymer and the API, quite fast dissolve in the body. So this is, and both at the same time, because we have a tablet that's a mixture of the two components. They are homogeneously distributed, the indomethacin and PVPVA. And what you see is here we take the tablet and it quite nicely dissolves in short time and releases the two components. So this is what we would like to see. And this is for a drug load of 0.1. So that means 10 weight% of indomethacin and PVPVA. Usually the drug load is higher because we want to have an amount that corresponds to a therapeutic dose. And we do not want to eat a cake, but a tablet. So we would like to have a small amount of polymer that carries the therapeutic dose, and usually drug loads for tablets are something like 0.3 or 0.4, so much higher than 0.1. So if we take such a ASD, where we have now a drug load of 0.3, that means 30% of indomethacin, and we do the same experiment, so we take this and we dissolve it in water, then we see that the release curves are totally different from this one. So what we see is that both PVPVA and indomethacin have a much smaller release as in this case. Even after 300 minutes, meaning after 6 hours, we are far away from the total release. So what simply means that the tablet didn't dissolve. What we also see is that now we have not the polymer and the API getting released at the same time as before. This is what pharmacists call a congruent release. And this is what they call a non-congruent release. So that means the two components which are homogeneously distributed in the tablet are not releasing at the same time and the same rate, but here the hydrophilic compound PVPVA is still released and much better released than the compound we would really like to get into solution. So the indomethacin release is quite bad and it's very, very small compared to what we originally had. And that gets even worse if we further increase the drug load. So if we are at 50%, that means now 0.5, it's getting worse and worse. So actually, none of the two components is releasing anymore, which means the tablet didn't dissolve, because 100% of the two components would be up here, and we are, you see, far below even 5 or 10%. So the question is, what happens here? What is the reason for this? And this is where we started to work on that. It gets even worse if we do not look at the relative release, but to the absolute amount of API released. So that's an experiment where we have the drug load is 0.1, and that means that assuming, or for the particular size of the tablet, that we had a sample that contained 6 milligram of indomethacin, 6 milligram of indomethacin. At the drug load 0.1, you can imagine the tablet was quite small. The rest, the other 90% at the polymer, and the indomethacin total absolute amount is 6 milligram. For the drug load 0.1, we see that this was the one where we had a release of almost 100%, meaning that after a certain time, all out of this 6 milligram is released into the water, into the aqueous system. So that means we had a release of 6 milligrams out of the 6 milligrams we had in the sample, which means everything was released. So now what we have seen on the previous slide, that increasing drug load means that we have a decreasing release in percent. So what one could think of, okay, let's simply increase the drug load, then we will have, if it's releasing worse, then we could simply maybe release the absolute amount simply. So what means if we go to a drug load of 0.3, we have 3 times the amount of the drug load 0.1. Now we have 18 milligrams in the sample. But due to the breaking down release, that means even after 5 hours, we have released only 1 milligram out of 18. So that means we have here 6 out of 6. We increased the overall amount to 18, but now we have not 18 out of 18, but we have even less than the 6 we had here. So that means increasing, tripling the drug load means that we have now almost no release anymore. And this, of course, for 0.5, it gets even worse. So we have now 5 times the amount of the previous sample of 0.1. We have now 30 milligram in a sample, and we still have only 1 milligram release as here. So that means increasing the drug load is not solved, does not solve the problem at all, but it makes the problem even bigger. And we have to take into account, or don't forget, that we are talking about very expensive compounds here. And so that means we increase the number of the compound, or the amount of the therapeutic compound. And what we get is the problem is getting bigger and bigger. And that also means what is not dissolved in the body will, of course, leave the body undissolved. It will end up in wastewater, and wastewater is, the amount of wastewater is, you can say, infinite high. So that means in wastewater, even those molecules will dissolve at the end, and they end up anywhere where we do not want to have them in our nature, in our so we do not want to have them end up in our food chain and anything. So it's really not only saving the problem that we would like to have these molecules dissolved in our human body, but we also do not want to have them in the wastewater. So that means that's a serious problem. And the question still is, where does this come from? So what we did is we went back to our storage problem. This is where I started with. So for the storage problem, we said we have our ASD, and storage means we have an environment. The environment has a certain relative humidity, so that means there are water molecules in the environment, and they will dissolve and will absorb in our ASD and cause the problems I have seen you at the very beginning, API crystallization or two-phase demixing. The RH was about 75%. The problem is if we think about what happens at dissolution. At dissolution, the RH is usually much higher than 75. It's very close to 100 even, because here, for dissolution, the surrounding is not air that contains water molecules, it's water. So that means we have the worst case, so to say, for the tablet is the dissolution process. The tablet is supposed to be dissolved in that medium, but at the same time, and this is what we certainly cannot avoid, is the water is, of course, from the liquid environment also absorbing into the ASD as before, but much faster and to a higher extent, because the RH here is close to 100. So that means during dissolution, we have not only dissolution of the tablet, but we have still, again, absorption of water. And this is what we then started to study from both thermodynamic and kinetics, because, of course, you have a dissolution process. It has a certain kinetics, and we have an absorption process, and this also has a certain kinetics. And so the question is, what is the faster process? This will certainly determine whether we end up having a problem, yes or no. And so what we did is we have now the ASD, and we bring this in contact with liquid water, and we considered the diffusion of all molecules in a system, meaning of the API molecules from the ASD into water and the polymer molecules from the ASD into water, but also from water moving into the ASD. And all this happens at the same time. So we had a diffusion modeling. We needed to get to the diffusion coefficients. And of course, the driving force for all this is thermodynamics. So we have had a combined modeling of both diffusivities and also phase behavior. And this, I will show you what the outcome of this modeling was. On the left-hand side, you see the same sample I was talking about before. This is PVPVA with indometacin. It was a clear sample at the beginning. We gave this into a water bath. And at the end, that means after 5 hours, we could see this. So the tablet looked completely different. So some things obviously happened here. And if we then took the tablet out of this metal ring, this is how it looked like. If you cut this in pieces, you can really see it has a core, an inner core, and it has an outer layer, and the two look quite different. And this is what we then got for the microscopic image. This is the ASD. Water comes from the right-hand side, so it moves in here. Whereas the two molecules, polymer and API, are diffusing from the left to the right. And what you see here is that the outer of the ASD, we really have we call it gel layer. This is where the water already moved into the tablet. And then we have the dry core, which the water didn't reach so far, and they look quite different. So what Dominic Bormann did is he calculated the concentration profile. So this is drug load as function of of the point where we are. So this is the inner of the tablet where we have the drug load, the desired drug load that we had in the tablet at the starting of the experiment. So this is still 0.3. Whereas the drug load is increasing, and that means at the gel layer, directly at the gel layer, we have a drug load of 100% almost, which means the modeling said at the outer area of our tablet, that means here in this yellow light area, we have an almost polymer-free layer where we have the hydrophobic API. And this very nicely also agrees with the experiment. So we analyzed the outer part of the gel layer, and of course we knew, and we still again analyzed after the experiment what the concentration in the dry core, which was still dry, was, and this was very nicely coincident with our modeling. So that means what happens is that during dissolution, water is absorbing and changing from the right to the left the inner of this tablet, whereas in regions where the water didn't reach so far, we see more or less the ASD as it was at the beginning. And as a result of whatever happens here, and I will show you in the next slide what happens here, we end up with a layer which almost only contains the ASD, which is very hydrophobic and does not want to get dissolved anymore. This is where the problem started. And it's getting even worse for higher drug loads. This is the same thing, but for higher drug loads, where you can see this was 0.5. This is the one which we still have in the dry core. And again, water comes from the right to the left. So this one, the dry core, is quite dry still after 5 hours. It's more or less unchanged. Nothing that happened here. And we have again a layer formed which more or less only contains exclusively the API. And of course, this does not want to get dissolved. And once you have this layer, and this layer doesn't dissolve, of course, nothing of what we have inside will ever dissolve. And this is obviously a problem if you take a tablet and it never dissolves in the body. This is obviously not what pharmacists want to have. This is was also observed by other people for other systems. This is again the same polymer. I said this is quite often used. And these are two different molecules. And what you can see is for molecules like naproxen, which is a fast crystallizer, you see really that you have some kind of crispy shell formed depending on drug load. And you can imagine once you have the crystals here, whatever you have inside will never get released, and so it's more or less done. And the same is for ritonavir, but here what was observed in literature is that we don't have a formation of a crystalline shell, but of an amorphous shell. And this again depends on drug load. So the higher the drug load, the worse it is. But what you can really see is that this is the inner of the ASD. You have a shell formed, and in the liquid we also have droplets formed. So there's obviously also phase separation at the also in the surrounding liquid. So, and this looks like a thermodynamic problem, and this is where we then start to look at it. So we have ritonavir, that was the molecule on the previous slide, and PVPVA, and it's exactly the same situation as before. As the higher the drug load, the smaller the release of the API, in this case ritonavir, and then at 40% drug load, and this is really a reasonable number, which is quite often used in for pharmaceutical products, none of the components releases anymore. So this is called loss of release or incongruent release, and of course nobody wants to have particularly this case. So we can even see how we could draw this back to a phase separation that happens in a system. This is again our Raman spectroscopy. And over time, we can really see that the system demixes. And this is now at very high relative humidities. This is not the relative humidity that's relevant for storage, but this is, we have chosen this because we would like to mimic an RH or surrounding of the tablet during a dissolution process. And this is the phase diagram. So this is what we use now to explain this behavior. This is the polymer, PVPVA. This is ritonavir. The dry system would be on this axis. And what we see, that's the solubility line of ritonavir in PVPVA, which is quite small. But ritonavir you have seen, is a big molecule, so usually it doesn't crystallize even if it's supersaturated. So that's not a problem in this case. But what we see is a huge miscibility gap. So ritonavir and water, they have a huge immiscibility. And even if we add PVPVA, this doesn't change a lot. So that means we have a huge miscibility gap. And that means that these samples here will demix. And this is our Raman measurement. So this is the starting point. What we did is we had a drug load sample of 35%. So this is, we started down here, 35. And then we added, we put the tablet into water. So that means it will absorb water. And depending on the amount, depending on the RH and temperature, it will absorb a certain amount of water. And that's a triangle. The triangle is the amount of water in the system PVPVA ritonavir that the sample would have in equilibrium. And then what you see is the black squares. These are our Raman data from the same picture, but now in this diagram. And what you see is, if we consider this as a function of time, we could really see the system demixing. So the system does demix this, and it not only demixes, but it demixes along the tie lines we have predicted. These are the dotted lines here. So that means the sample does what we thought it would do after absorbing water. It would move from a point down here, which is homogeneous outside the miscibility gap, but absorbing water during dissolution at very high RH, we will move into the demixing area, and so the system will demix. So this is the same system. And now, why does demixing sometimes lead to a breakdown in release and sometimes it doesn't? So this can be explained on this phase diagram. This is, if we have a small drug load, this was the smallest we considered was 20%, meaning 0.2. We would start here. The sample is homogeneous, everything is fine. We bring this in contact with liquid water. So that means during dissolution, we move up here. And so that means we will enter the miscibility gap and, for example, end up here. And that means if we are in a miscibility gap, we get two phases, a ritonavir-rich phase and a polymer-rich phase. And then we have the lever rule, and that means we have much less of the ritonavir-rich phase compared to much more of the polymer-rich phase. And this looks like this. So what you see here is, this is a tablet. This is a dry system. This corresponds to this point. Here we have water from the dissolution medium. This enters the tablet, brings us up here, and then we get two phases. And we have a lot of the polymer phase and a little bit of the ritonavir-rich phase. So we can imagine this like droplets of ritonavir-rich phase in the continuous phase. This is what we would get for small drug loads. So what happens if we increase the drug load? The diagram, of course, is exactly the same. The only difference is that we now have a higher drug load, and we start from a point more to the right in this diagram. And again, we add water to dissolve the tablet, and then we move up here, and we end after we have the water is absorbed to the equilibrium in the system, we end up here. And then again, we have, of course, a demixing. The difference now is that we have almost equal lengths of these lines, meaning amounts of the two phases. So this gives us a different morphology compared to the one for smaller drug loads. And this might look like this. So we have now not droplets of one phase and the other, but we have something, and this could also be seen via microscopy. We have now a system that looks more like this. We have domains really of both the Ritonavir-rich phase, which is the red one, and of the polymer phase. And we should not forget that the red one is the hydrophobic, so this will not like to dissolve in water where the polymer would. And so due to these different morphologies, we observe different dissolution behavior. This is the 0.2 case where we have, this is a dry tablet, this is a gel phase, which already absorbed water, where we have the phase separation in the system, but we still have, or we do have a release of the droplets. But according to the previous picture, if we are up here, so in the dissolution media, we have, of course, a huge amount of water, and we are still, as you see, we are still in the miscibility gap. So that means that the immiscibility doesn't stop here. We still have droplets also after dissolution, but this is fine because they do not crystallize, and that means that's why we don't call this dissolution but release, meaning that we have now droplets, Ritonavir-rich phase droplets in the body fluid, in the aqueous body fluid, and they will then release the API Ritonavir. So this is something which is okay, and this is the release behavior that we observe for that case. For the higher drug load, 0.3, we have different amounts of the two phases, as I said before. So that means this is the gel phase now, and the polymer is getting released from this gel phase, but the Ritonavir-rich phase does not. So this is what we have also observed in our experiments, that we have this shell forming, and this shell, after a while, once all the polymer is released, will not contain any polymer, but what is kept, or what is left behind, so to say, is the hydrophobic compound, and this does not want to dissolve. And so this will stay there, and all what's inside will never get dissolved. So the problem is, how can we solve this problem? How can we overcome this situation? And the idea of our cooperation partner, let's add a surfactant. So indeed, most of the ASDs on the market do also contain a surfactant in addition to the polymer and the API. So the idea was to add a surfactant, but this is again still the phase diagram as before to see. This were our Raman spectra that we have taken from the samples for the 0.3 case. And this is, again, the samples are very nicely in agreement with the tie line as before that we predicted. So now the idea of adding surfactant. So this drug float is the same, but now we have a third component in the ASD, which is a surfactant, up to 3 weight%. And this indeed really improves the dissolution behavior. So we have a similar picture to the one at 0.2 and no surfactant. So we could get back to the nice case, so to say, by adding a surfactant and keeping the high drug load. So 0.3 is a higher drug load, and this is more or less totally released once we add surfactants to the system. The surfactants also release these other triangles, the green triangles you see here. They are here behind the blue symbols, meaning that the surfactants is also totally released. You can see here that's in the system. So it's also what we monitor. And the idea is that adding the surfactant stabilizes the small droplets of the Ritonavir-rich phase. So we have a behavior which is similar to this one, and so a morphology is very similar to the one at low drug loads, and so we have also a similar release behavior. Okay, and then the idea was, okay, what happens if we increase now the amount of surfactants? Can we maybe even make the things better? So can we maybe even increase the drug load? can we now go from 0.3 to 0.4? And if we add a surfactant, then get the same as before? And the answer is no. So what you see here is this is drug load 40. And the idea was, okay, if we go from 0.3 to 0.4, we should maybe increase also the surfactant, as amount of surfactant, increasing from 3 weight% to 10 weight%. But unfortunately, this does not work. So what you see is we have similar behavior to the one we had here with a drug load 0.3 without surfactant. The API is only released to a very small amount. About 30% only is released, the other one is not, whereas the surfactant and the polymer is released, particularly the polymer, the surfactant is not totally released. So what happened here? What happens? The surfactant did work at 3 weight%, but it doesn't work at 10. So what about the morphology back? And what we see, and I will show you the Raman map on the next slide. What we see is if the amount of surfactant is too big, it forms a third phase. Instead of stabilizing the droplets in a two-phase system that we had at low surfactant concentrations, we now, as we have 10 weight% of surfactant, we have forming three phases. One which is ritonavir rich, then the blue one, which is rich in a polymer, and a surfactant rich phase, which is the green one. And if the surfactant is forming a separate phase, it doesn't care about stabilizing the droplets anymore, and so we have our old problem back. That means surfactant is nice, but it does not help if we have too much of the surfactant in it. And the explanation again is a phase diagram. Let's look at thermodynamics. This is this one. We now have four components. We have the PV, PVA, ritonavir, and water. This is what we had before, but now we have also the surfactant. And so we did a PC-SAF calculation, and indeed, PC-SAF calculation suggests that we have a demixing in three phases, as we assumed looking at the release profiles, and also the experiments say this. So this is Raman spectra taken from different points in a sample. It's a map as before, and what you see is that we don't have not only points between the two phases formed for the surfactant lean case, but now as we have 10% of surfactant, we really have three phases not only predicted, but also the experiments say the system is moving and it is trying to demix into three phases. And so surfactant does not care about stabilizing the two phases anymore, but wants to be in its own phase, so to say. So this, again, was a nice explanation. And of course, it depends. Everything depends on the kind of surfactant, on the polymer and ritonavir. And so that gives a lot of things to do, a lot of phase diagrams to predict and to find maybe a better polymer or a better surfactant for a given API. And also not only to choose the components as such, but also the right composition to get the targeted release behavior. So this is what we say. A certain amount of surfactant is fine. It stabilizes the ritonavir-rich domains. If the amount is too low, it cannot prevent forming the two phases and this morphology, and we will not have nice dissolution of the ritonavir. And if the amount is too high, we have three phases, and this is then still not what we want to have, because we will have no release of ritonavir of the API, or at least very low only release in this case. Also in the other, so there is a certain window of surfactant compositions that do the job. And this brings me to the take-home messages. What I've shown you is that water really is the enemy of ASDs. It might cause API crystallization and or water-induced demixing in the ASDs, and this obviously causes problems during storage, but unfortunately not only during storage where we could avoid having water, but it's even causes bigger problems during release because we cannot avoid the presence of water during release in body fluids, obviously. So that means that, depending on the systems and the phase behavior, there might form a hydrophobic shell, and this can decrease or even inhibit the API release, and this is obviously not what we want to have. And if we understand this based on a phase diagram, we can, of course, do the calculations and also predictions and suggest the components that might help to avoid this problem. And overall, the final solution is the more is not the better. We find this obviously also in our daily life, and this applies to surfactants. They have a certain window. It also applies to the APIs because we also do have a certain window only for particular drug loads where we can find stable conditions. And with this, I like to thank my group and also our sponsors. And of course, I really like to thank you for your attention. And I'm here for any questions you might have. Thank you very much.